Hello, my name is Erica from Mustang Math, and today I will be doing a lesson on states in counting and probability. What is a state? A state is simply an intermediate stage of an event. For example, the teams are tied 7-7, I'm currently 4 blocks away from the store, or I've rolled the dice 4 times and I haven't rolled a 6 yet. Some key concepts that you'll be able to take away today are states are often described using state diagrams, and I'll go over how you can construct those. Also, states can often simplify complicated casework and organize scenarios. Now, let's get right into the problem. This problem reads, a cricket randomly hops between 4 leaves, on each turn hopping to one of the other 3 leaves with equal probability. After 4 hops, what is the probability that the cricket has returned to a leaf where it started? So let's try to interpret what this problem means in math terms. First, let's label these leaves, call them A, B, C, and D. And then, without loss of generality, let's say the cricket begins on leaf A. Then, at any given turn, it has a probability 1/3 of moving to some of the other leaves. Okay, so that's pretty simple. What if we tried to simulate a round of what's going on? For example, one of the possible outcomes could be A hopping to B, and then D, and then back to B, and then A on its 4th hop. So this would be a scenario where the cricket does return to a leaf where it started. In a different situation, maybe the cricket hops here, here, and then back to A. And then on the 4th hop, we see that it is forced to move to one of these 3 other leaves. So it cannot possibly return to a leaf where it started. So maybe it hops to D, and then we end up with it not satisfying the condition. So that would be part of the probability that we don't want to calculate. Okay, so this problem is a little bit complicated, but the way that we will be able to use states to tackle it involves looking at it with a bit of symmetry. We must take advantage of the symmetry of the fact that on any given turn, the cricket has an equal chance of moving to the other leaves. So maybe we can just view these leaves as a single block. Let me show you what I mean by this. We will describe 2 states, a state where the cricket is at A, and then a state where the cricket is not at A. Well, how is this helpful? We can actually complete this diagram by thinking, well, on any given turn, as we just saw, if a cricket is at A, then it has to move to one of these 3 other leaves. It has no other choice. Therefore, we can simply say, well, the probability that it moves from at A to not A is 1. Here we're constructing, this is called a state diagram. Oftentimes, the states themselves are written in circles or squares with a little label, and then they're connected by arrows with the direction of the arrow representing which direction we're moving in. In this case, we're moving from at A to not A. Finally, the probability is often drawn as a number on the edge of the arrow. Okay, let's continue filling out this diagram. We still clearly haven't mapped out all the possible cases. What if we're at not A? Well, let's think. Let's say the cricket is here at C. Where can it move? It can move to B, to A, or to D. So it has a 2/3 probability of staying in the not A state. That is when it moves to B or D. Likewise, it has a 1/3 probability of getting out of this situation and moving back to at A. By the way, this state diagram is really powerful in the fact that it doesn't depend on any singular round that we're on or hop. It's in any situation, these are the probabilities. This is what makes it so simple in describing complicated scenarios. Notice that I've used a little circular arrow to describe a situation where we've made a move, meaning that we've made a hop, but we're still staying in the same state. Okay, so we have a state diagram, and it's much nicer to look at than all the 4 leaves. But how does this actually help us in advancing in solving the problem? Well, oftentimes in combinatorics, when you're faced with a problem that seems very abstract, it is helpful to assign some variables so you can use algebra to gain some footing. For example, let's say we call AN the probability that cricket is on A after N hops. And then let's define Bn to be the probability that cricket is not on A after n hops. See, now clearly we have a relationship between these states and the variables we picked. And by the way, note that this little subscript helps us distinguish between different A's, because obviously the probability that the cricket is on A after 1 hop is not the same as the probability that the cricket is on A after 2 hops. Note that our desired final result is going to be A4, because we want the probability that it has returned to A, its starting point, after 4 hops. Okay, so what else do we know about AN and BN? Note that there's something critical that we can find. AN plus BN must equal 1, regardless of the value of n. What does this mean? This means that after n hops, the cricket must either be on A or not on A. This seems intuitive, but this is helpful in giving us a relationship between AN and BN. Well, how else can we find a relationship between AN and BN? Actually, we can use this diagram right here. Note that AN is equal to 1/3 BN minus 1. Why is this true? Well, we can see this from looking at the diagram. We can see in this arrow, when we're moving from not A back to at A, there is a 1/3 chance of moving in this way. But we have to spend 1 hop in order to complete this arrow. So that's why the subscript here is n minus 1 and the subscript here is n, meaning that we can relate the previous turn to the next turn. Okay, similarly, we can also find a value of Bn that relates to An. We see that Bn is going to equal 2/3 Bn minus 1 plus An minus 1. So why is this true? Well, we see this is the little circular arrow when we're stuck in the same situation. We've spent 1 hop, and there's a 2/3 chance that this situation occurs. The An minus 1 occurs because we must move from moving from the n minus 1th hop to the nth hop while we're at A requires us to move to a not A leaf. Okay, finally, this is a recursive relationship that we can use to just write out the first few values. Because 4 is still a relatively small number, we can simply work from the bottom up. Let's draw a little table. So this is the hop. It could be, we only need to go up to 4 because that's what the problem is asking for. Note that the 0th hop is simply the starting situation. This is before we've made any hops at all. And then this will be, the hop is the same as n, by the way. This is An and this is Bn. Okay, so before we started, since we've already said, again, without loss of generality, that the cricket begins at A, then An, or A0, must be 1, because the cricket must be there. Likewise, since the cricket obviously isn't starting on any of the other leaves, B0 is 0. Next, on the first hop, the cricket must move from A to B, C, or D, like we've described. So Bn must be 1 and An is 0. This could also be found using these relationships, but this way is just easier. Okay, now we can begin actually using our equations that we have. We know that An is, or A2, is going to be 1/3 of B1. So this is simply 1/3. And we also know that An plus Bn equals 1. So this is 1 minus 1/3 equals 2/3. And I'll write that just 2/3 so it's easier to look at. Okay, so now An is going to equal to 1/3 of this. Because, again, from our recursive relationship, so this will be 2/9. And then An plus Bn equals 1, so this is 7/9. Finally, we find from the same logic that A4 would be 7/27, and we can still find Bn even though it's not necessary. It would be 20/27. And again, remember, we're simply looking for A4, so our answer is just 7/27.